That was a great presentation on the STEAM objective. So I know if I have questions on the experiment, I know exactly who I'm going to go and talk to. So the next speaker that I'll introduce to you today is Brian Hebert. And Brian will be giving a 6-minute presentation on the STEAM calorimeter experiment that we conducted.
How y'all doing, guys? I'm Brian Hebert, and I'll be presenting on the STEAM calorimeter experiment that we did last week. These are a few of the main points I'll be speaking on today. First of which is quality of steam. Quality of steam is the ratio of the mass of vapor to the total mass of steam. And the objective of our experiment was to find the quality of the steam coming in our experiment apparatus. So here you can see the apparatus we used. If you follow the color-coded arrows, you can identify the components of the experiment. Coming in, our steam coming in is the red arrow where it enters the separating calorimeter. The black arrow is the liquid water that's drawn out through the principle of inertia. And continuing on out through the yellow arrow is dry steam, which is of a much higher quality than what's coming in. And also at the yellow arrow, going into the throttling calorimeter, we have an orifice where the pressure drops, which drives the steam into the superheated state. So here you can see the process on a TS diagram. We start off with the steam coming in. At state 1, you can see the quality is about around 50%. Once we leave our separating calorimeter, you can see the quality is much higher, almost around 95%. And once we leave the throttling calorimeter, you can see where the steam is driven into the superheated region. And from here, once we know our pressure here, we can find our temperature of saturated vapor in state 4, and from there we can find our enthalpies. First, the enthalpy of saturated vapor at state 4, and then assuming temperature 3 is equal to temperature 1 coming in, we can also back out our enthalpies of state 3. And also assuming that our orifice is adiabatic, we can assume that state 3, the enthalpy of state 3 is equal to state 4 here. So we can set these equal to each other and back out the quality at state 3. So the second set of equations we can use to find our main objectives, quality at state 1. We use a mass balance of the system. We're assuming that the mass of vapor entering at state 1 is equal to state 3 after we remove the liquid. And also we use the quality equations with the mass of vapor. And then our mass balance M1 equals M2 plus M4, assuming that M4 is equal to M3. And then finally we can find our quality at state 1. So the results I have here, our quality at state 3 was about 96% with a standard deviation of 4, so there's not much fluctuation right there. Whereas the quality of the steam coming in was about 46% with a standard deviation of 13, so there's a pretty good fluctuation in quality of steam coming in. And this is we're the only section in Monday, so I used the data from the previous Tuesday's lab, and they had their quality of steam coming in was about the same as ours, 45%. with a standard deviation of about 17 or 18. So they had a little bit more fluctuation than we did. And here you can see Tuesday's lab plotted in white, whereas ours is in yellow. And you can see the fluctuations throughout the day of the quality of steam coming in. Here we have the same plot with the temperature throughout the day also plotted. And as you can see, the temperature didn't fluctuate that much, whereas the quality of steam fluctuated a good bit throughout the day. So it's hard to say that there's a correlation between outside temperature and steam quality. So in conclusion, the qualities that I found were subject to some sources of error. One of the main sources I saw was the mass flow leaving the separating calorimeter, the liquid mass flow. As we were doing our experiment, you could see in the sight glass the level would jump up and down, and it was pretty erratic. So I think, I had to use an average to get a good measurement of that. So I think that's some source of error. Also, there could be error in our measuring devices, pressure and temperature sensors, and also the assumptions that we made in the calculations, the adiabatic orifice and mass balances. There could be some error in there. So that's it. If you guys have any questions.
What do you think causes the variation in the steam quality throughout the day?
One hypothesis I had was looking at, if we look at the temperature here, it's about 60 or 70 degrees. So I was thinking, most of the users of our steam on campus is probably heaters. So that day, there probably wasn't too much usage. So maybe because of the low usage, there could be some, a lot of water or condensate backed up in the lines. So that's one thing I thought would maybe make the quality fluctuate a good bit. Any other questions?
Could you talk about the separating and the floating calorimeter?
Just like the concept behind it? I'm not sure what. Well, the separating calorimeter, as I said, you can see here, the main function of this is to remove most of the liquid water in the incoming steam line. So that uses the principle of inertia. There's some 90-degree bends and 180s, and the liquid water can't make those bends, so it hits the walls and falls out. And that's our mass flow here. And the dry steam continues on. The function of the throttling calorimeter is to drive the steam into the superheated region so we can get pressure, and once we get pressure and temperature readings there, that allows us to back out our enthalpies for our equations.
So can we use any of them interchangeably, like have the floating before the separating calorimeter?
No, I think they serve pretty different purposes. Our throttling calorimeter includes an orifice with the function to drop the pressure and superheat the steam, whereas the function of the separating calorimeter is really to remove water. There's a lot of bends and things to where the liquid water can't make it through. Any other questions? All right, thanks guys.